So it is about, we might need much of this stuff. Okay, let me just, this is function theoretic, right? There you.
Yeah. And there is also another word of
So it was about a Hecke thing. So we have this d mod Bun-G, and here we have this int-co nilp of log cis. So as was remarked, well, quasi-co always acts on the nilpo. So it's a monoidal category that acts on this. And so here, so now we use this naive Satake to have, well, so tautologically Sf run acts on this. But, so there was naive Satake which made rep gcheck run act on it. And so as far as the Sudamam's question is, well, can you repeat your question?
quasi-co acts on both sides.
You mean, so, but okay, now the claim is that quasi-co acts on this side. But the claim that the fact that it does, it's a non-trivial assertion. So as was discussed today's in Nick's talk, so let me just, okay, let me just keep this for a second because we might need it. So we have this rep gcheck run. So it's connected by a pair of adjoint functors. Log cis gcheck. So there is a left adjoint, which is kind of, well, more or less tautologically constructed by evaluations, well, using the wrong kind of jet interpretation, so on. And so it has, for, again, more or less tautological reasons, a right adjoint. And it's a proposition, not very hard one, that this right adjoint is fully faithful. Okay, now, so this acts on this. And now you can ask the following question. Yeah, and both categories are monoidal, and this is a monoidal functor. So this is fully faithful. You can think of this as some kind of Verdier quotient. So this is a quotient of this by some kind of big kernel, very big.
And then the other one is not monoidal.
Pardon? The other functor is not monoidal. So the right adjoint, the one which is fully faithful, is not a monoidal. But this one is monoidal. And, well, and again, where is Yuval? I don't know where.
Tell us what you're doing. You're saying that.
Well, exactly. So Yuval, not here, but he was asking me, so you should think of this as some global Galois datum, and this is global Galois data, and this is local Galois data. And so you're saying that global Galois data sit faithfully inside local Galois data, but you don't know who they are. It's very difficult to identify. So I don't know how to say what I'm killing. The kernel is very, very large, but we don't know don't have any explicit handle on it. However, so here comes a non-trivial assertion that the kernel, whoever this kernel is, when I act by this kernel on D of Bun-G, it acts by 0. It's what's called the vanishing theorem. And because of this theorem, due to this theorem, you know that the action of rep gcheck on Bun-G actually factors through the action of quasi-co. So as a result of this, now D of Bun-G is a module over this guy as well.
Was this theorem discussed?
This theorem was not discussed. No. Why was it not discussed?
Theorem, like, do you need this theorem to, for the Langlands correspondence, or will it derive it from Langlands correspondence?
Well, first of all, it follows from Langlands correspondence. So I think it's used at some stage of the proof. So when you actually do this proof, you'll be, well, before you do it, you'll prove this pretty easily. This vanishing theorem is, so the kernel of this left adjoint functor, when you act by it on D of Bun-G, it acts by 0. So we didn't state it because there was no occasion for it. And it's kind of a deep result. It's like,
But is your quasi-co with one or without one?
which quasi-co?
On the
No,
right.
no, it's quasi-co of log sys g check. It's a quasi-co and it's a finite dimensional object.
There's no, okay.
And see, it's a very surprising assertion. Just I give you a quasi-coherent sheaf with log sys g check, and using it, I can define an endomorphism of d of bun g. It involves Langlands duality. Like, why should you be able to do this?
But that's an example to be very close to the Langlands duality itself.
Well, but it's not.
I mean, it's not only because you have a different quasi-coherent.
Well, how do you know that this action, for example, doesn't factor through some closed subset? In principle, you could have.
Of course, but if you want to construct a function in one direction.
Yeah. Well, the function in one direction, that's more or less how it's constructed.
Wait, so is this structure easy to extend to higher levels with the action?
What do you mean higher levels?
If you it's a ramified situation.
Well, it'll be log sys with punctures.
Yes, but the action you will still have the action.
Yes.
You don't have a formulation in terms of two and categories, I guess.
Yeah, I will still have the action. And no, you can. Your level doesn't interact with.
So you can have any level structure at any number of points.
Yeah.
This you really want.
The action, yeah. And so for this reason, it's pretty amazing. So like d of bun g, so just having this action tells you that d of bun g can be spectrally decomposed with respect to log sys g check. So it lives over log sys g check. In other words, there exists a sheaf of categories over log sys g check whose global section is d of bun g. So it's kind of it has some content. All right, that was Amnon's question.
Will the proof of this theorem be discussed?
Well, we were not intending to. We can in some.
Basically, what you said now, that this is one of the main steps.
Well, we can. So to do this proof, we have to do. To do the proof, we have to go through localization, Nick's talk tomorrow, and my Oprah's talk. So a logical time to do this proof is just before Dima's last lecture.
So let me just.
Or during.
So then I understand correctly that the way it's proved is that you construct enough d-models in one chip which generate everything, and then you kind of explicitly check on those.
Yeah, exactly. So yeah, you construct enough generators, and you show that the kernel kills those. And there are two kinds. There are Eisenstein guys, about which you know by induction, and there are guys that come from Kac-Moody, about which you know basically by the balance and Dirichlet construction. It's not very difficult. It's also pretty easy. So this theorem is not difficult, as it turns out. It doesn't have any of this nightmarish technical stuff with log sys. Pardon? Well, it doesn't have. So you don't need to prove Stam's thesis for this theorem. All right. So our idea is to have a free Q&A without any particular agenda. Dima has an agenda, but we can. So it's derived Satake. It's again super cool. It's derived Satake business, but we can live without it. We'd rather answer questions.
What's the, I mean, you still haven't spoken about the global proof, but what's the relation of this with other approaches which use something like trace formula?
Trace formula? But I mean, there is no trace formula in the geometric theory. Say again?
Not even philosophically?
I see. I don't know. I have no idea.
Aren't the Stukas something like orbital integral?
Well, Stukas are see very deeply in characteristic P. We don't have any kind of analogs of Stukas here.
And also, we don't need trace formula there, as Vincent Lefort explains us.
Yeah. So again, so historically there were only two kind of ideas. So one was what we're doing now, embed into Whittaker, and the other was use Kac-Moody. And neither quite did it. So what we're doing, we're combining the two, and together they kind of just enough.
But the global part of it is the use of Kac-Moody. It's the fact that you somehow in geometry you are able to construct enough automotive representations by hand.
Yes, the whole idea is that indeed, not only on both sides, you have enough objects on both sides of the correspondence, where is it? That you can control.
And these objects are eigenobjects, right?
Well, no, eigenobjects if you, well, eigenobjects if you start.
No, I think it's exactly if you don't know how to construct eigenobjects explicitly, it's not construct.
No, wait a second. So again, eigenobjects, so what's an eigenobject? You fix a local system and you work over it. Well, I don't want to fix it, I want local, I don't want to work at the skyscraper. Like, I do work with families. Again, so the whole idea, as will be discussed, these objects will be I will start providing these objects in my talk, well, in an hour, half an hour. Nick will continue, and then this Oprah's talk will actually finish constructing these objects, and then Dima's talk at the end will show how to use it. So indeed, the whole idea is that on both sides, you had produced many objects which you can control. And these objects do not come from, they don't have any analog in number theory. They're not kind of, well, they're not Whittaker related to anything. They do come from Kac-Moody. So you basically kind of, here it's the first time that you're using, you remember that we work with D-modules and not just sheaves. So namely, D-modules that can be constructed by generators and relations. And at the end of the day, this Kac-Moody construction, that's what it does. You really construct, well, in a very high-tech kind of fancy way, but at the end of the day, these D-modules are given by generators and relations. Something which you can't do for sheaves over Atlantic.
And a priori, they are not eigenobjects. If you don't know that these things live over log C, you cannot.
No, so, but I don't understand your insistence of eigenobjects. Again, what do you mean eigenobject?
No, but let me answer at least.
But just let him answer. Ask the question, then he'll answer. What do you mean eigen?
Eigenobjects for the action of the
So eigen meaning for a given eigenvalue?
Yes.
So why do you want to do it? Like, why do you want to fix a local system, particular?
You know, what is it that you construct classically? I mean, it's very easy to write down an automorphic function and very hard to write down an automorphic form.
Okay, so what you can do, okay, I don't want to do it skyscraper by skyscraper, but in this construction, we do control. So we know now that both sides are acted on by this.
You said that you're going to use this construction to show this also.
Let me just say, so both sides are acted on this, but when we construct our objects here on both sides, we construct them in such a way that the action of this on both sides coincides. We do control how they behave spectrally with respect to this. Yes, you can later.
But what you cannot do is that you cannot construct eigenobjects just for a given local system. There's no explicit construction.
Well, yes, there is.
What do you mean by that?
Well,
That's something like a smoothie side, which is not.
no. So, you see, already having this action, I can construct for you plenty of eigenobjects as follows. Pick your favorite object here and start an act on it by the skyscraper. That will be an eigenobject. You can do it.
And you don't need your theorem for that. Just you can.
No, you do, because I mean, how do you know that this acts on this?
No, it's valence and spectral projector.
At the end of the day, but I mean,
You know it's an eigenobject, you just might get 0.
yeah, well, it's not, yeah. So at the end of the day, this construction is balanced and spectral projector construction.
No, that I understand, but it's not what I meant. I mean, this construction with localization doesn't need explicit. So you don't know what to localize here.
What do you mean localize? Localize?
I mean, if you localize Kac-Moody representations,
Well, you do.
this thing by itself. doesn't
Okay, you don't know that every local system comes from an opera. Is that what you mean?
Well, okay.
If you found an opera that corresponds to a local system, you can, well, we haven't discussed that yet, so not everybody knows what operas are. You can produce eigensheaves. Yeah. Okay, so let's, yeah.
You're looking for something global. Why not look
Between what and what? But I mean, it's non-commutative. Well, essentially, what we want to do is for Yemukai, but it's non-commutative for Yemukai. At the end of the day, that's what it is. Alexei?
Suppose you have your correspondence for any recursive group tree. What about the Langlands factorialization?
So many people, for some reason, are asking this question today. So So Langlands functoriality, from my perspective, I don't know, I may be wrong, it's not part of the game for the following reason. So, okay, the story that we're doing here admits what's called a quantum deformation. So in this case, you'll be considering twisted D-modules here, and this int-co, quasi-coherent local system will also become twisted D-modules. Now, this Langlands functoriality does not survive. So even if you have, if you have G1, G prime check mapping to G check, well, on the level of local systems, well, you have locsys G prime check mapping to locsys G check. You can take the direct image and say, okay, we have this functor on the Galois side. Let's see what it does on the spectral side. However, when you quantumly deform, you lose this functor as well. So, I mean, I think Langlands functoriality is much more kind of, it's a kind of accidental phenomenon that happens specifically at this degeneration. And what we're doing.
Sorry, this is not what you told before.
Yeah.
You told before simply that we don't have a factor because the direct image doesn't preserve the importance condition on the spectral side.
No. So I gave two reasons, and I'm giving kind of the more substantial reason. So you see, kind of, again, I view both as part of like a family when you vary the level. And at this particular point, some more phenomena happen. But what we're doing this week is kind of insensitive to this particular phenomena. We kind of, basically what we're doing amidst this quantum deformation. For that reason, kind of, I'm not a big fan of Langlands functoriality.
But first, for example, if you have a map of, let's call it H check to G check,
Yeah.
then would you have a functor from intro-nilp locsys G check?
No, not a priori. So it doesn't preserve the nilp condition either. So
At the level of quasi-coherent, do you have it?
Well, I have direct image.
So you can hope for some functor between the
Yeah, I mean, but I don't have serious hope that this functor will be kind of easy. Well, can be described in some manageable way.
And just for the support, I think in Arentine talks that there is some relation between the singular support of the push and the original.
Yeah. You can control it, but it will fail here. You see, even such a basic thing as direct image from the torus, even that we don't have. So if you want to just map the torus to a G, so what's the functor do you expect? So there is a very nice functor. It's called the compactified Eisenstein series. But it's not quite the direct image. It's what I described. Okay, maybe I can repeat what I said. It was on day one. And this functor is trickier than just direct image. So say you want to go from the Cartan to G. What can be more basic, right? And you expect some kind of Eisenstein series. So the functor on the spectral side, and there is a nice functor on the geometric side. It's called compactified Eisenstein series. So I'm going to tell you what this functor is on the spectral side. So we have the following category. We have int-co nilp locsys G check. So now we have quasi-co locsys G check. Okay, let me just write this. So this functor xi int-co locsys B check. Sorry, it's B. And here we have, that sits inside all of int-co locsys G check. So here we have this functor P int-co lowest star. It's int-co direct image. So the claim is that if you precompose it with xi, it actually maps to this condition with singular support. So that was the theorem that Dima stated. This estimate from above on singular support tells you that if you take here guys with zero singular support, if you push them down, they require not more than nilpotent singular support. Okay, now here is that functor on functoriality. So you map locsys T check to locsys B check, just embedding. Call it I, and you do the quasi-co direct image. You do quasi-co direct image here, and then you do this int-co direct image further. And that's your functor. And let me just say that it's not the same as if you did quasi-co direct image to quasi-co of localized check and applied Xi. That would be a very different functor.
So what should be the right one?
Pardon me?
What is the right one?
So this is the right one. So this is not the right one. This is the functor that admits a nice geometric description. It admits a geometric description which is parallel to what happens in number theory. This Eisenstein series procedure, which we know in number theory is the functoriality map, corresponds to this weird functor. Let me just emphasize, there are two more functors, neither of which does what you want. You can do quasi-co direct image all the way and embed, or you can first embed it to int-co and do this. And that will be wrong.
But Dennis, you seem to be actually making a case opposite to the one you want to make, because you're saying, here's how you do functoriality for...
Yeah, you do functoriality for the torus, but it's not just some naive direct image. You go through the Borel in some tricky way.
So what? But then it's saying that maybe there is functoriality, but you have to first understand it on the spectral side.
So I'm saying it's just direct image on the spectral side will not give you any map which has a chance of having an easy description on the geometric side. So that's all I'm saying.
Can you ask any question?
You can ask any question.
What is the, so if I take constant sheaf on band G, what is the analog on this?
Okay, it's a great question. So in fact, Vincent had a conjecture, and we had a proof of this conjecture. Does everybody want to know this answer?
Maybe
It's it's some kind of spectral. It's a spectral Whittaker coefficient. Something that it's totem phantom, but it. So it's first of all, it's a guy that will completely kill quasi-co, as it should, because you're dealing with a constant sheaf on Bungie, which is kind of the most Whittaker degenerate guy possible. Okay, so I'll start writing the functor, and then I'll stumble. So first of all. So, yeah, it'll be orthogonal. So instead of that object, I'll define, okay, let me just say something. So it's a fact of life is that this category is also self-dual. So like it's isomorphic to check. So instead of describing that object, I will describe the pairing with this object. It will be a continuous functional from here. And this functional is, in fact, the RAM cohomology of the compact supports. So, in fact, it's a... So, okay, we're going... So, exactly. Arbitrary. Arbitrary. Okay. So, usually, cohomology of compact supports on all D modules, if you're dealing with algebraic varieties, with schemes, it's only defined on proper schemes. You can prove, well, it's a functor which is left adjoint to upper Schrick, and you can show that this left adjoint does not exist unless your scheme is proper. But for some stacks, it does exist even without. For example, if you take the stack which is the vector space modulo GM, yeah, on such a stack, this functor cohomology of compact supports does exist. So the claim is that Bungie is also like this. So this functor of upper Schrick does admit, for non-trivial reasons, left adjoint. Okay. So let me just say it. So there is a non-trivial pairing, and it's really non-trivial. It's to vect. Pardon? No, first of all, it's covariant.
It's covariant both.
Yeah, and so the cohomology of Bungie, usual cohomology, is not a continuous functor because Bungie is not quasi-compact. You do something else. It's this functor that Drinfeld introduced. However, so it is canonical self-equivalence, and so if you have any no, it's non-trivial. It uses this. Yeah, it's non-trivial functor. So you can, again, look at this paper about compact generation. You'll see it's called pseudo-identity. It uses the compactification of the diagonal. It's a non-trivial guy. Now, if you have any object here, you can consider a functor of the second variable just pairing against this object. So if as the object you use the constant sheaf, the functor that you will get will be cohomology with compact supports. Okay, so this is the functor that I want to describe spectrally. Again, its information is completely equivalent to this functor information of the constant sheaf. So here is the functor, and again, I'll stumble. Okay, so okay, yeah.
Can you repeat the question that you're actually giving an answer for?
Pardon me?
Can you repeat the question you're?
So
okay.
we've got this functor. Pardon?
So he wants to know for the trivial local system.
No.
No, the other for the
No.
module.
So here there's a constant D module.
Okay. Yeah.
So what corresponds to the spectral side? So here is the functor, and this functor is supposed to kill quasi-co. So here's what it is. So you take int co with nilp support, log sys. Well, then you embed it into entire int co of log sys, and then you do the following series of the following functors. First, you do upper shriek to int co of log sys b check. Okay, that's one thing you do. So then let me continue. I don't remember the answer offhand. So then you do direct image on the following. So int co on, so the guy that appeared in Dario's talk, log sys b check modulo the commutant of m check. So this is the product of Borel subgroups for copies of PGL2. So this group, if you take, it's a Cartan. Well, let me also take B adjoint. So project it to the adjoint group. So, okay, so this is product over vertices of the Dinkin diagram, log sys of the following group. It's GM semi-direct with GA. So on each one of those, I'll describe a functor to vect. It's a pretty funky functor, and it'll look like the Whittaker coefficient. It's already beginning to look like the Whittaker coefficient, doesn't it? All right, so where is the... Okay, so... let's just geometrically, so I have log sys, this semi-direct product. So it maps to log sys GM, and that receives a map from just point mod GM. So now I'll take the fiber product. Log sys GM, and here will be point mod GM. And so now I'll do the following operation. I'll pull back to here. So I'll apply pull back, and now I'll write a functor out of this category, okay?
No, here you assume that the torus is quite small. Not small.
No, I killed. I passed to the adjoint. Take direct image on B edge. All right, so now this is the category that I'm interested in. Now, and so what's my stack? It's log sys with respect to the additive group GA modulo GM. So this is what I'm interested in. And I want to write down a functor from here to vect. And I will produce this functor in a moment. So who is that functor? Okay, now comes the moment of truth. What is log sys of GA? So naively, this is H1 of our curve, but considered in the GG sense. So this is, well, let me take cohomology. Okay, I should say it like this. So, well, it's cohomology of my curve, the RAM cohomology, well, constant coefficients shifted cohomologically by 1. So I want to perceive it as a DG stack. What do I mean? So cohomology, there is 0th, 1st, and the 2nd cohomology. So let me just slightly non-canonically, I'll write it as follows. It's the art in stack 1 point divided by k, which is h0, times the algebraic variety, just the vector space h1, times, well, exactly our favorite spec of eta, degree of eta is -1. And that is this h2. That's what h2 does. All right. So, well, this decomposition is non-canonical. However, canonically, it maps to this guy. So this algebraic, well, the stack maps to this factor. And I'll take the direct image. So finally, I'm left with the following. I'm considering the following category. So it's int_co of, well, again, our favorite guy, degree eta equals -1, and I'm taking the GM equivariant part of it. Okay, now who is this? So I claim this is vect already. So namely, let's apply Koszul transform. So this will be modules over the symmetric algebra, well, modules over k of xi, where degree of xi, okay, so it's not int_co, I'll kill it. Okay, the next is 2. And I'm taking not just modules, I'm taking graded modules. Now, if in this if in this category you kill modules that are supported at 0, i.e. if you invert xi, then it will be vect. So this by localization, it maps to modules xi inverse. And this category is vect. So see, the last step explicitly kills everything that was quasi-co. So under this Koszul transform, pardon?
Is the singularity category?
Well, it's exactly the singularity category of this guy. Graded, yeah. So you exactly kill the guy with supported 0, which was the quasi-co part. So that's Van Saun's functor.
So is it right to say that this is somehow evaluation at the derived principle level, right?
Who is saying that? Oh yes, I'm just yes, exactly. It's some kind of derived shifted principle nilpotent, as it should be. That's what we know. That's Yours theorem for the affine Grassmannian, which is a particular case of this for P1. So Van Saun looked at it for P1, and then he kind of, well, he was able to write this formula for an arbitrary curve. So that's what happened. Any more questions?
So in this diagram that you erased, it was there. So you explaining about Eisenstein function.
Yeah. Yes?
So there is a yet beta Eisenstein function. I heard. What does it correspond to on the?
Better meaning?
So involving bond B, right?
No, that's not better. It's no, it's not better. It's so there is a usual non-compactified Eisenstein series, which is the following functor. So there's int_co log_sys d check. There is quasi-co log_sys b check, and so this is int_co direct image, and there is q upper star, well, q upper shriek from quasi-co. Q upper star, quasi-co log_sys t check. So this is just it's Romka, this is for you. This is eyes shriek using non-compactified guys. Now the question is, what do you get if you use bond B rat instead? So first of all, it will be functor from where? It's no longer functor from bond T. It will be functor from this category of bond B rat that Dario introduced. So bond B rat was the closest stratum in his extended Whittaker model, and this is this corresponding category. It's this category WGB. It's a functor from this category.
WG
GB. So he had the stratification of the extended Whittaker model by parabolics. And that's the closest stratum. It's, if you wish, that's the recipient of the constant term. So, and again, it's a different category. It receives a map from D of Banti, but it's larger. So you can ask, what does that correspond to on the spectral side? And it's the category that will be discussed, well, be the main actor tomorrow. It's kind of main actor in Sam's thesis. You consider quasi-coherent sheaves on Loxi's Bichek equipped with a connection along the fibers of this map. So instead of starting here, you start here, but not just quasi-coherent sheaves, but quasi-coherent sheaves equipped with a connection. And so that's the main category, that's the ultimate source of Eisenstein series. You take de Rham direct image to here. So that's why in Nick's talk we started talking about this weird guy, D modulus log cis. Why on earth? Well, exactly because you have something de Rham going on, but we just didn't let him get there. All right, so I think it's...
Yeah, very quick question. So you
yeah.
mentioned this quantum magnetic Langlands. Why does this condition nilpotent single support, why doesn't it appear there?
No, it does. We just don't know. So see,
Don't know the formulation.
so for generic values of a parameter, it doesn't appear. For let's say integral values of the level, I don't know the precise formulation. I have to tweak the name for.
I don't think that's the literal formulation.
But so to say, on both
Just
sides.
let me just say. So I won't vouch for it.
But it's not that you have some clear reason why it's not.
Let me think. I might have an answer for it. I thought about it, but I'm forgetting this. I might have an answer in a couple of hours. Just give me some time. It may be the case that it's actually true as is. Yes, please.
Yeah, I just wanted to say we have D models on both sides.
We have D models on both sides.
What do you mean by singular support?
Exactly, but you might have to tweak the category of D modulus a little bit. You might have to add some more compact.
Is it somehow more interesting if you don't? Somehow, what sort of happens when you do information?
I'll think about it and I'll give you the answer, okay?